Hi everyone. This is Dr. S. Venkateswarlu, working as a professor of EC at IARE, Hyderabad. Today we're discussing about what do you call that digital filters. Under digital filter, impulse response of digital filter can be divided in two categories. One is IER, impulse response, infinite impulse response, and FR, finite impulse response. Okay, so the formula corresponding to the general case described by the equation below, while the later occurs when n is equal to 0. We have to observe this mathematical notation. Okay, so with this, so we will try to analyze this all digital filter. We are concentrating only what you call IER filter. So with this, that IER filter is designing. So many methodologies are there. We have to concentrate on impulse invariance method. So based on that, we are ready to analyze this. Okay, this digital filter. Yeah, design of IER filter, impulse invariant method, infinite impulse response filter using impulse invariance technique. Today we will concentrate on this particular design. Okay, design of infinite impulse response filter using impulse invariance techniques. Okay, in this we have to observe this IER filter is designed such that impulse response h of n of digital filter is sampled version of the impulse response of the analog filter. So the transform of the infinite impulse response is given by h of z, where here it is that h of z with h of z is equal to, where we know that the summation where n is equal to 0 to where n is equal to 0, what do you call 0 to infinity. Okay, with this h of n, where h of n into z power minus n. Here we are right to what you call concentrated on this impulse response. So IR filter is designed such that impulse response h of n of digital filter is the sampled version of the impulse response of the analog filter. The jet transform of infinite impulse response is given by h of z is equal to the summation n is equal to 0 to h of n into z power minus 1. Like this, we should follow this, where h of z at z equal to e power n into s into t. It is also equal to that what you call, where h of z at z is equal to e power s into t. That it is also equal to that what you call the summation, where n is equal to 0 to what you call 0 to infinity. Okay, with the impulse response h of n, impulse response with h of n. Okay, product with this into e power minus s into tn. Like this, by using this all jet transform, the infinite impulse response is given by these two equations. Okay, so let us consider the mapping points from the s plane to the z plane by the relation where z is equal to, where z is equal to e power s into t. Okay, here we have to substitute that s value, that s value is ready to substitute, where s is equal to what you call, where s is equal to that sigma plus j omega. Okay, and express the complex variable x in polar form, where that z is equal to r into e power j omega. Okay, like this, where r into e power j omega is equal to e power sigma plus j omega whole power t. So that here where r is equal to e power sigma into t, where omega we know that sigma into t. So like this, using this all analysis, mathematical expression for this, so where it is r value and omega value of that r into j omega and so on, easily can identify that therefore the analog is mapped. The analog is is mapped to a place in the jet plane of the magnitude e power sigma into t and angle sigma into t, capital T. Like this, we have to observe this design of IAR filter using impulse invariance technique with the IAR filter designs such that the impulse response is h of n of the digital filter is sampled version of the impulse response of analog filter. With this, after using this, they will transform the infinite impulse response. Infinite impulse response is given like this. So, using this all impulse response, there is a fundamental aspect or basic level of the impulse invariance to choose an impulse response where impulse response is it is followed by what you call h of n. Okay, for the discrete time filter that is similar in some sense to the impulse response of the continuous time filter. Okay, if the continuous time filter is band limited, then the discrete time frequency response will closely approximate the continuous time frequency response. Okay, like this, based on this all fundas of the impulse invariance method or technique. So here the relationship between what you call the continuous time and what you call discrete time frequency is linear. So from this, consequently, expect for the aliasing. Okay, after that, the shape of the frequency response is preserved with this impulse response method. So here it is, we require that the impulse response of the discrete time, or you can consider the digital filter be the discrete version of the impulse response of the h of s of the analog system, or you can consider the filter, hence the name impulse invariant. Here initially that h of s, here it is given that h of s with the transformation, it is given to the h of t. Okay, after where it is the t is analyzed where t equal to n into t. Oh, it is given to the h into that impulse h of n into t after applying this jet transform where x of t is h of z. So that means to remove that sampling effect, you can consider 1 by t into delta of t minus n into t. Like this, these are the what you call the impulse response of the discrete system to be the discrete version of the impulse response of the analog system. Here we have to follow these all steps. So first get h of s, here it is. Here get h of s, continuous time transfer function of analog filter that satisfies the prescribed magnitude response. This is the followed by step 1. Next, so apply the inverse Laplace transform. Apply inverse Laplace transform to get the impulse, to get that impulse h of t. Okay. Next, third. This is the first and second. So third one is obtain the discrete version of h of t by replacing t by n into capital T. N into capital T. We are going to observe that one, what you call h into n into t. Okay. So next, this is relevant to the third. We're coming to the fourth step. Apply the jet transform to h into n into t to get that what you call finalized h of z and multiply by capital T. Like this we should follow. Directly we are right to observe that where n is or n is equal to initial to 0 to infinity n value. After that we are right to verify that all h of t n versus h of t h of n. So where h of t is like this and h of n of t is like this. So in graphically we are right to verify that graphical representation. How we are evaluating, how we are determining this impulse invariant method while we are designing this IER filter. Okay, infinite impulse response filter. Okay, so with this, so we can consider the best example of this using the invariant impulse response method. Design a digital filter that has shown the pole zero distribution. Pole zero distribution. So with this, so we have to consider this h of s is equal to what do you call s plus a. Okay, s plus a with this by s plus a plus j omega naught and s plus a minus j omega naught. Okay, so where h of s is equal to s plus a by s plus a square plus omega square. Here according to this, so where after applying the previous steps and all, first what we observed here, second first step is this one, second step apply the inverse Laplace transform. Okay, after applying the inverse Laplace transform h of s is equal to e power minus at into cos of omega naught n t. It is also equal to h of t. Next, coming to the next step, h of n into t is equal to e power minus a n into t cos what do you call omega naught into capital T. Okay, like this third step also we have to use this one t into what do you call, it is mentioned that t into z of, okay, z of h n into capital T. Okay, this ready to analyze this one where it is also equal to that 1 minus e power minus a into t into cos of omega naught t into z power minus 1 by 1 minus 2 into e power minus a t cos of omega naught t into z power minus 1 plus e power minus what do you call 2 into a into t z power minus 2. So whole product with this capital T. After that we have to verify that all h of z. So that h of z is how we are recognizing h of z. Apply the z transform of the h into n into t to get the h of z and multiply it by capital T. That's why it is mentioned that one. So multiplied with the capital T. Finally, that h of z is equal to t minus e power minus at into t cos of omega naught t into z power minus 1 by 1 minus of 2 into e power a minus at into cos of omega naught t into z power minus 1 plus e power minus 2 into at z power minus 2. Okay, like this we try to analyze using this invariant impulse response method, design a digital filter, the shown pole zero distribution. Okay, finalize that all h of z, where h of z is equal to t minus e power at, okay, into t into cos of omega naught t into z power minus 1 according to previous step. Now it is simplified. Okay, so we will try to analyze this same mathematical equation into the sequence of this, where a naught is equal to what do you call that this value where a naught is equal to what is that capital T, where a1 is equal to that a1 is equal to minus e power a into capital T into cos of omega naught into t. Okay, this where b1, this b1 is also where b1 is like this, where minus 2 into e power minus a into 2t into cos of omega naught t into t. where B2 is equal to e power minus 2 into AT. Okay, like this, try to analyze that easily can observe that example of IER digital filter with this what do you call impulse invariant impulse response method, right, to design. Okay, next steps to the discrete time filter design by transforming the prototype continuous time filter. In this case, so obtain the specification for the continuous time filter by transferring the specifications for the desired discrete time filter. Second, find the system function of the continuous time filter. After that, transform the continuous time filter to derive the system function of the discrete time filter. Like this, try to verify that. With this all steps, these notations, steps you have to follow. How many steps are available here? 3 steps are available. Concentrate on each and every step, try to analyze. Okay, with this, impulse invariance with the Butterworth filter. Best example is this, we can consider this best example. So here it is, impulse invariance with the Butterworth filter. Okay, specification for the discrete time system or discrete time filter. Here it is given that specification. Okay, first specification is like this. Second specification, let TD is equal to 1. What happens here? That omega is equal to omega sigma into TD equal to omega. Assume this effect of aliasing is negligible. This is the important aspect. If you are using this condition, okay, assume that the effect of aliasing is negligible. So now it is the notations are changed. The specifications are changed. 0.89125 less than or equal to mod SC of J omega, mod less than or equal to 1, 0 less than or equal to mod omega, what you call less than or equal to 0.2, where mod SC of J omega less than or equal to 0.17783, okay, 0.3 pi less than or equal to mod omega sigma. Okay, like this, the impulse invariance with a Butterworth filter, we have to follow this on the thing. Okay, next, impulse invariance with the Butterworth filter, they are providing this type of specifications. Okay, how it is varies in mathematical and graphically, supposed we have to verify. Okay, like this, based on this typical value, rightly we try to analyze that how it is designed and manually, where order of the filter is how it is affected, and that omega c is value is it is reflected with the order of the filter or not, with the help of the impulse invariance with the Butterworth filter will be observed. So with this, here it is. After that, we try to analyze that imaginary axis, real axis, how it is varies. If it is in order of the filter, SK values increases. This is all we have discussed in previous level. Okay, like this, in impulse invariance with the Butterworth filter. So here it is, SC of S is equal to SC of S and SC of minus S is equal to what you call 1 by 1 plus S by J into omega C whole power 2n. Now it is also equal to omega C into 2 power n by S into what you call 2n plus omega C power 2n. So where SC of S is the poles pair, if you have to consider that one, minus 0.182 plus or minus J 0.67679. Next, minus 0.497 plus or minus J 0.497 minus 0.679 plus or minus J 0.182. Of that H of S is ready to analyze using this all mathematical notation where it is reflected. Finalize that all H of C of S is like this. If the TD value is 1, okay, so how it is reflected? The TD value is 2 and 3 and so on. So easily can analyze that all this impulse invariance filter with a Butterworth filter in a digital filter, we write to using this all best example. Easily you can analyze this all particular case. Okay. So coming to the IAR filter design with the bilinear transformation method. Infinite impulse response filter design. This is also digital filter. We're using that all second methodology or bilinear transformation method. So steps for the design procedure. We have to follow this all digital filter specifications and transformation with the frequency wrapping. It is given to the analog filter specification. After that, we will try to verify the transformation by the low pass prototype filter. It is also given to the analog filter transfer function. Here we are trying to verify the bilinear transformation. Final outcome is digital filter transfer function and frequency response verification will be done by using this all steps of the design procedure. Based on this all procedure, we will design that IIR filter using bilinear transformation method. After that, we'll try to compare that impulse invariance and bilinear transformation method. Which one is the best for practical aspect or industrial oriented is you can analyze. That's why we are learning these two methodologies, bilinear transformation method and impulse invariance method for designing IIR digital filter. Okay. So in binary transformation method, you have to use that frequency wrapping. You have to observe that by using for low pass filter and high pass filter. So that frequency wrapping, okay, is equal to 2 by capital T into T tan of omega, what you call omega D into T by 2. For band pass filter and band rejection filter, we have to use that all wrapping is this particular what you call formula, mathematical notation. After that, we have to verify that obtain the digital filter transfer function. Okay. If you are concentrating on the binary transformation method, we have to use this all procedure where h of z is equal to h of s, where s is equal to 2 by capital T z minus 1 by z plus 1. Okay. Like this, if we are using this from the analog low pass to desired analog filter, it is followed by HP of S. Okay. It is low pass prototype. So after that, try to verify that analog low pass filter with the omega c is the cutoff frequency, S and S by omega c. After that, it is fed to this value, and second level S stands to omega c by S. It is where omega c is the cutoff frequency, which is given to this high pass filter S. So analog high pass filter it will come. And like this, they are following this a band pass filter. Analog band pass filter will be observed, and analog band stop filter it will try to observe by using the bilinear transformation methodologies based on this particular procedure. Okay. Finally, this is our prototype transformation. Frequency wrapping is next level is prototype transformation will be observed. Okay, under this, so graphically by use this all particular design, we will expect that all graphical representation where analog low pass prototype transformation into a low pass filter like this, where V versus HP of J omega JV. Here S is equal to S by omega C, and that is analog to what you call analog low pass prototype transformation into low pass filter. Okay, so like this, center frequency and bandwidth we easily can try to observe, but this facility is not there in impulse invariant methodology by bilinear transformation. So center frequency and bandwidth and analog low pass filter prototype transformation to the band pass filter, how it is in graphically and numerical values try to observe, especially bilinear transformation method. Excuse me. Here, under bilinear transformation, can avoid the problem of aliasing. If you are using what you call impulse invariance method, this is not available. In binary transformation maps, maps minus infinity to what do you call minus infinity to less than omega less than equal to infinity onto minus pi less than equal to omega less than equal to pi. Bilinear transformation S is equal to 2 by 2d into 1 minus z power minus 1 plus z power minus 1, where h of z, that h of z is equal to sc into 2 by 2d into 1 minus z power minus 1 plus z power minus 1. It is also equal to sc into of s, where s is equal to 2 by 2d, 1 minus z power minus 1 and 1 plus z power minus 1. Okay, so like this s value right to measure. So finally that z value is right to measure after designing the binary IIR filter by using the binary transformation method. So where s is right to observe like this mathematically, where sigma less than or equal to 0 mod z less than or equal to 1 for any omega. Okay, if sigma greater than or equal to 0 mod z greater than or equal to 1 for any sigma, like this. Okay, normally that by using this all mathematical notations are like this. Now in terms of this binary z transform or BZT method, here we can consider the term STZ, okay, and S and S1 and Z, where STZ here impulse invariance method, we can consider that binary z transformation method. Easily right to compare this one. Left side is the ITZ, impulse invariant method. Okay, here S and S1Z is binary transformation method. It is the most important method of obtaining the IIR filter coefficients. In the BZ, what you call bilinear transformation method, the basic operation is to convert an analog filter H of S into an equivalent digital filter H of Z by using the bilinear approximation. That is H of S, SD of S, where Z is equal to, we know that Z is equal to e power st is equal to e power st by 2 by minus e power minus st by 2 is equal to 1 plus s into t by 2 and so on, by 1 minus st by 2 plus and so on. Okay, we can consider this is the first order bilinear approximation. Therefore, the z is approximately equal to 1 plus what do you call s plus t by 2, 1 minus st by 2. Okay, like this, where z value ready to analyze this one, and z minus z into st by 2 is equal to 1 plus st by 2, z minus 1. Okay, that is z minus 1 is equal to what do you call z plus 1 into t by 2 into s. Okay, therefore s is equal to approximately, where therefore s approximately 2 by t z power minus 1 by z power plus 1. Okay, here it is sd of z is equal to h of s by at s equal to 2 by t into z power minus 1 by z plus 1. Like this, right, to verify distal frequency is identified, and wrapping effect is also identified. Before the pre-wrapping wrapping effect is also identified. There is a facility here that S value j into omega or omega a or omega a is it is equal to pre-wrapping effect is affected or not. Maybe here by using this omega is, it is considered a distal filter. How it is wrapping effect is involved or not is going to analyze by using this all methodologies. After that we go for this, it is the recursive and non-recursive way to identify. So now that frequency wrapping effect BZT. So here in this case, the effect of the binary transformation is called frequency wrapping. Every feature appears in the frequency response of the continuous time filter appears as it is the frequency response of the discrete time filter at different what do you call frequency. Here distal frequency versus analog frequency, how it is reflected. when minus infinity less than or equal to omega a less than or equal to infinity, the time at interval minus pi by t less than or equal to omega less than or pi by t, where what you call sigma s domain with j omega and j sigma here, that response is like this. To compensate for this, every frequency specification in the design has to control over omega, what you call c or omega 1, and has to be pre-wrapped by the setting with what you call omega, setting with compare with the in equation 1 and equation 2. In equation 1, here it is S is approximately equal to 2 by t z power minus 1 by z plus 1. Coming to this equation, omega is equal to 2 by t tan into sigma into t by 2. Okay, so like this, the binary transformation with the z value and real axis, imaginary axis, z plane, and what you call imaginary axis, how it is appeared with this z is impacted with this imaginary and real axis, where it is z value is assigned and js value and e power j omega is equal to this particular value. Yeah, the binary transformation method is to analyze the mathematical expression j omega and s value. If we know these all two values, right, to analyze that all, what you call omega. Finally, that where omega is equal to sigma and omega is analyzed that with graphically that omega versus that sigma easily can analyze that graphical representation of a particular bilinear transformation. Using this all, directly we are trying to design with digital filter, IIR digital filter variation using this particular, easily right to compare these two methodology, impulse invariance and bilinear transformation method. So there is a relationship between frequency response of SC of S and H of Z. Like this, try to verify. And comments on the bilinear transformation. So it avoids the problem of aliasing encountered with the use of the impulse invariance. Okay, it is non-linear compression of the frequency axis. Okay, like this z plane and s plane will be appear like this. Okay, so this where minus pi by what do you call this, s plane 3 pi by td and pi by td. Now how it is appears with the z plane, how it is interact with the z plane and s plane, and minus pi by td. Like this, the comments on this remaining comments, the design of the discrete time filter using binary transformation is useful only when this compression can be tolerated or compensated for, as the case of the filter that approximate ideal piecewise constant magnitude response characteristics. Okay, now we are to compare this comparison of the impulse invariance and binary transformation method. The use of the binary transformation is restricted to the design of approximations to filter with piecewise constant frequency magnitude characteristics. This is a major comparison, and such as high pass, low pass and band pass filter if you are using the binary transformation method. Coming to the impulse invariance, can also design low pass filter, but here in binary transformation method, high pass, low pass, band pass filter is so with piecewise constant frequency magnitude characteristics will observed by using like using the high pass, low pass and band pass filter. While you are using the impulse invariance, can also design low pass filters. However, so it cannot be used to design high pass filter because they are not band limited while you are using the impulse invariance. Okay, so like this we are going to compare. One more, binary transformation cannot design filter whose magnitude response is not piecewise constant. Okay, next, so like binary transform such as differentiator. However, in coming to this impulse invariance method, can design a band limited differentiator. Okay, so with this we are to verify this designing methodologies, the comparison by designing IIR digital filter using the impulse invariance and binary transformation method. So by using this all, you can ready to decide which method is relevant to our education applications or maybe industrial oriented, and all easily ready to analyze this particular comparison. Of that, you ready to design your own what you call specification or different specification or given specification or whatever it is. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.